Morning everyone. Today we are going to learn how to solve the questions in complexometric titration. And this question is about the condition for direct and accurate titration of metal ions. So now first, let's have a look at the question. So you are given this concentration of EDTA, and it is used to titrate calcium ion. So this titration, it is said that should be carried out at pH 10, not pH 5. But for zinc ion, it is okay to be pH 5. The question is why? Why calcium can be carried out at pH 10, not pH 5, but zinc can be at pH 5? So let's think about it. So do you have any clue for solving this question? Say something. Anything is okay. Any idea about why pH is important in complexometric titration? Why? Because what?
Because in the complexometric titration, we need to consider about the acid effect.
Acid effect.
Right.
Acid effect of what?
Acid effect of EDTA, teacher.
Yes, because in complexometric titration, EDTA has acid effect, and this acid effect will affect our final product, right? So now let's have a look how this acid effect will affect our product. This is a reaction equation in this titration, and M stands for metal ion, Y stands for EDTA, and My is a product. This is a main reaction in this titration. Then let's talk about the side reactions. So first, let's have a look at this Y, which is EDTA. So what kind of side reactions of EDTA?
It has acid effect and coexisting ion.
It has
Acid effect.
acid effect and what?
Coexisting ion.
Coexisting ion.
Yes.
Yes. And what is this N?
This one is the other ion in EDTA.
Other ion in EDTA?
Yes.
How can metal ion in EDTA? Just free. See anything.
Teacher, it is interference.
Interference.
Yeah. It's interfering metal ion
Yeah.
in the solution, not EDTA. EDTA is a chemical, right?
Yeah.
Okay. So now we know for Y we have two side reactions, acid effect and coexisting ion. Next, let's talk about M, metal ion. Then how about metal ion?
It has
What kind of side reactions relating to M?
OH minus.
OH minus, which is called what?
hydrolysis. Hydrolysis.
Yes, it is called hydrolysis because metal will react with OH to form this hydroxide. Okay, this is one side reaction of metal ion. What else?
Uncommon interference.
Interference.
What
Interference.
else?
Ligand.
What?
Ligand. Other ligand in the solution.
Are the ligand in the solution?
No,
Do you
teacher.
agree?
Buffer that we use in the titration.
So one says ligand in the other ligand in the solution. Another one says the buffer used in the solution. So which is right? Which is right? What do you think? Any idea? Any opinion?
Not sure.
Yeah, anything is okay. What do you think, Bobo?
I think ligand.
What?
I think other ligand.
You think the ligand is right?
Yes.
At certain extent, both are right. Both are right. Because when Zhang Di said ligand in the solution, people will ask, where does this ligand come from? And this ligand comes from the buffer. So both are right. Okay, so the ligand you see here, ML, and we call it complexation of M with other ligands. Okay, so these are the side reactions of metal and EDTA. Then MY, the product. What are they? What are the side reactions of MY?
OH minus and H plus.
Okay, yes. So with H and with OH. So we call these reactions side reactions. So another question. Side reactions of M and Y and side reactions of MY. Which are good for this main reaction and which is not? So this is a main reaction and this is a side reaction. So for side reaction, sometimes we know that side reaction is bad for main reaction. But in this case, how about them? Any memory about these side reactions? So the main purpose, we want to get MY, right?
Yes.
So now, since M and Y will have reactions with other species, not with M or Y, then the side reaction of M and Y will not be good to form MY, right? Because they will go to other places to react with other species, not with M or Y. But for MY, when MY react with hydrogen or hydroxide, the amount of MY will be reduced, and the reaction direction will move to right side. And this will be good to main reaction. Okay, so now we can know a little that the side reaction of M and Y is bad for main reaction, but the side reaction of MY is not. Okay, so now we can know the side reaction of M, side reaction of Y, and side reaction of MY. They have different effect to this main reaction. And until now, you may ask, we want to know why some complexometric titration can be titrated at pH 10 or 5. Then why we are talking about this? Why we are talking about this? Why we need to know clear about this to find out which pH is proper for the titration?
I think we want to control the stepwise reaction in EDTA.
Yeah, we want to know the exact side reactions in this titration system, right? And when we know these side reactions, we can know more about what? We can know more about so we have a reaction equation, right? And for each reaction equation, we will have a reaction constant, right? So for m plus y equals my, we have this k and y, right? But in different conditions, we have different side reactions. So in complexometric titration, we have a new concept, which is here, conditional formation constant. And for this conditional formation constant, we have a equation. So this equation is this. So based on this, we can know that whether this titration can be directly and accurately titrated. So that's why we want to know this k and y prime. So we need to calculate k and y prime and then calculate CMSP to see the product of these parts, whether they are larger than 6. So if at pH 10 or at pH 6 or at pH 5, if this result is larger than 6, it means at this pH, this titration can be titrated directly and accurately. Okay, that's why we need to get a little review about this formation constant. So first, let's see CMSP. CMSP means what?
It means the concentration analytical of method at
Stoichiometric point.
At SP, right? So in this question, just now we said that the metal ion, the concentration is 0.02, right? So at SP, what's the concentration?
divide to 2 teacher.
Yes, divided by 2, which is concentration is 10 minus 2 mole per liter, which is 0.01, right? And then if we replace CMSP by 10 minus 2, then we can get what? Then we can know K prime my log should be larger than 8. So this comes to the question of how to calculate the conditional formation constant. And then we know that K prime equals to log K. Log K is a formation constant, and K prime is a conditional formation constant, right? And here, alpha m, alpha y means what? Alpha m and alpha y. It is
Coefficient
activity.
louder.
We are discussing teacher.
Yeah, discussing.
Activity of metal and activity of DJ.
Activity.
Yes.
嗯 activity. So the rest agree with activity.
Activity.
một trăm và sau đó một cái
Positive concentration alpha activity.
Just now we talked about the side reactions, right? So alpha m and alpha y must relate to side reactions, right? So here, alpha m, alpha y is what? They are what?
Coefficient.
It's so
masking
reminder.
reaction.
it's a coefficient.
Coefficient.
Coefficient. So alpha m is what? Is what coefficient? So please check your book to find out what is alpha m and what is alpha y. As a reminder, they are both coefficient. So have you found any clue about what are alpha m and alpha y?
Slide on. Chị cả đấy.
They are coefficient, right?
Alpha is a complexation effect. Complexation effect.
Complexation effect. Complexation effect of m, right?
Yes.
But for side reactions of m, not only just complexation, it also has hydrolysis, right? So if you combine these two together, we call them what?
Trong nhà sử dụng tiếng Anh. Hydrolysis effect and
Coefficient.
Yeah, they are coefficient. And they are what coefficient?
the name là
What?
I don't remember.
You can remember.
Yes.
Okay, in fact, I said the answer many times. Alpha m is the side reaction coefficient of m. Side reaction coefficient of m. Okay, so alpha m and alpha y. So now here we come to the question of how to calculate alpha m and alpha y at different pH, right? Remember, at pH 10 and pH 5. So now, how to get alpha m and alpha y?
That's on table.
So we need to search the data from the table, right? And yes, so if we can check them. So first, if we check in the tables, we can find the following data. First, the KCAY. They are formation constant, right? Formation constant, we can find them from table. And then at different pH, we can find out alpha YH and alpha zinc and alpha calcium. And also we know the concentration of metal ions at SP. They are both 0.01 mole per liter. And then if we use this data, we can go to the final result. And according to this equation, we can know that at pH 5, you see, log KCAY prime, it is smaller than 8. But for zinc, it is larger than 8. And at pH 10, both of them are larger than 8. So you still remember the question? The question is, why calcium can only be titrated at pH 10, but not pH 5? So here we can see that because the conditional formation constant of calcium Y is smaller than 8. So that's why we cannot titrate calcium at pH 5, right? And for zinc at pH 5, at pH 10, both is larger than 8. So that's why we can titrate zinc at both pH 5 and pH 10. So that's how we solve this question. All clear?
Còn áp phím cùng.
Okay, good. That's all.